So today we're going to be covering an introduction to the machine learning concepts, the types of learning, and we're going to see how to frame a machine learning project. And then you will see what is that we're going to follow on the week 2, week 3, week 4. So in the week 2, we're going to learn all about the common machine learning algorithms, techniques on how do we handle the data, how we need to um, split our data for the training. We're going to talk about how should we play a little bit with our model to be able to get the most optimal output. And what is very important for you to know is that on the today we're not going to code. We're just going to see a lot of um, explanations of concepts and so on. But starting next week, we're going to do some coding every week. And we're going to do some exercises. Some of them are going to be, we're going to be using Google Colab. So you will need a very basic knowledge of Python. So if you haven't worked with Python, I will highly recommend you to go maybe spend some time between this session and the next one, maybe doing a couple of tutorials. Very basic knowledge is what you really need. I might send something on the Discord later to share some tutorials that you can follow. You also need. We're also going to be working with web machine learning, which is like it's not brand new, but it's a very recent application of machine learning on web technologies, and it's really nice all of having access to all of these different platforms, right? And being able to introduce machine learning in web projects is really amazing. So for that, we're going to be using TensorFlow JS. So you need a working knowledge, basic working knowledge again of JavaScript and HTML, a little bit of CSS as well. But I'm going to be sharing that afterwards. So on the week 3, we're going to learn about how to evaluate our model, how to evaluate the performance of our models, and what can we do to improve the performance of the model that we are going to create. And then on the last day, the last session, we're going to be talking about neural networks. What are they? What are the different types of architectures of neural networks? We're going to be talking about TensorFlow JS as well, and some exercises, really nice applications of TensorFlow JS, and you will see how easy it is to use. All right. So let's begin. What is machine learning? So in order to understand what is machine learning, we should really talk about artificial intelligence, right? And it's important to understand that it's a field of computer science, and the main goal is to create machines that are capable to think and to act and to behave like a human, and that's the main goal. And then in artificial intelligence, there are different types of artificial intelligence, or different types of methodologies or frameworks um, to be able to reach that goal of mimicking the way humans can think and learn, and can reach conclusions and do decision making and so on. And I would like to share with you um, what are the types of artificial intelligence. And this classification that I'm going to talk about is one of many, but is one that you're going to be hearing about it a lot, um, everywhere. So let's talk about that a little bit. So the types of AI, we will find the artificial narrow intelligence. So maybe you're reading an article somewhere and you will read narrow intelligence. So what is that? So basically, narrow intelligence is machine learning. Is what we have right now in the industry. So it's basically you have a model, a software that can work and can mimic the reasoning and the decision making process, or maybe the speech, or many other things, like a human. But they work just in one area, on one domain, on one problem. So, for example, that can be we can have a machine learning model that can, or an AI agent that can play Go, for example, and that agent can be really, really, really good at it, and it can even be better than a human, but which has been the case, right? But that agent cannot, is very good in that domain. It cannot be good at, I don't know, creating recipes for cakes, right? It's a different domain. So that's what we have right now. We have a bunch of narrow intelligence and narrow intelligence solutions, which can be machine learning solutions that are very, very good at their own areas, but they cannot generalize. It's not that you can bring one and use it to very different in a very different domain. So the next stage is the artificial general intelligence, which is also called AGI. So you will hear also a lot about this, about AGI. So what is AGI? Is when a machine, when an artificial intelligent agent can be as smart as a human, right? And we will call that machine intelligence. And some people will call that machine intelligence, but that's the goal, to be as smart as a human. And for example, now that ChatGPT has been out and everyone is talking about that, very recently, and it's not recently, but for example, OpenAI, I think it was last week, they in their blog they posted something about how are they really working towards achieving artificial general intelligence, achieving AGI. And if we achieve AGI, is like I said before, the machines are going to be able to generalize their knowledge, and they are going to be able to work in different kind of domains, maybe not for the ones that they were specifically trained for. Um, so there are many people that believe that we will never going to reach AGI, and there is a lot of people also, very important artificial intelligence researchers, that are working towards AGI, and they really believe that we are going to achieve AGI. Some people say that is going to be very soon. Some people say that it's going to be by mid-century. Nobody really knows, but there is a lot of very big companies investing a lot of money in trying to achieve AGI. Okay, and then the next type will be the artificial superintelligence. And this is a point where this is the type of artificial intelligence that uh, will happen when a artificial intelligent agent would be much smarter than the smartest human, right? And it's something that many people is scared of, and there's is something that a lot of people is saying we should prepare for that, because one of the things that some of these researchers say is that when that point comes, we are not going to really understand what is going, like all of the advancements and the discoveries that the machines are going to make. We're not going to be able to understand them, and that it can be something like one Nobel Prize every 3 minutes, and we are just not going to understand what is it about. So yeah, there are a lot of people, again, some people say this is never going to happen. Some people really believe that. So yeah, these are the types of AI that you might hear and you might read about. You might hear about it in discussions about ChatGPT, or the future of AI and the future of machine learning. I really wanted you guys to have like like an overview and an understanding of what are the types of AI. Okay. Um, so now let's go to machine learning. So machine learning is a branch of artificial intelligence, a branch of computer science, and is like it says here is an approach to achieve artificial intelligence through systems that can learn from experience to find patterns in a set of data. So you have a bunch of data and you want to find patterns in that data in order to learn and to make a prediction, or maybe you want to classify something. So that is machine learning. And basically, machine learning, what we do is that we are teaching the computer to recognize those patterns by giving them sometimes a lot of examples. And instead of like writing, programming the specific rules, and these patterns are always found within the data. So when I say like a machine that we want a machine to learn, it doesn't mean that it's just a robot, right? It can be software, and so yeah, basically, machine learning is about creating algorithms that learn very complex functions or patterns and from a set of data and make predictions on it. So, okay, we can see something here. Is teaching the computer to recognize patterns instead of programming it. So, what does that really mean? So, let's have a look at this. So, in traditional programming, the way we program right now, we have data, we have a program, a set of rules. Maybe we coded a program to calculate, I don't know, the time that takes to go by train from Glasgow to, I don't know, to Madrid. And we have some data about the trains, about the routes, about the how fast can a train go. And then we give that to the computer. The computer grabs the data, grabs the algorithm that the program that we wrote, do the calculations, and it gives us an output. It can say, well, getting from Glasgow to Madrid in train can be, I don't know, 20 hours or whatever. But in machine learning, it's different. In machine learning, what we do is that we give the data to the computer, right? And we give the output, right? And then the machine learning algorithm, the model, will come up with a program, which is the model, right? And that's the model that we're going to use to then give new data to get the output. So it's kind of we're creating the program. It's a different approach. All right. And there is I found this really, really fun example. And let's have a look at this. And the credits are for Daniel Burke, and you can find him on Twitter on Mr. D. Burke. This is a very fun example. So what do we do with traditional programming, right? We have the ingredients, which can be the data. We have the vegetables, and we have a turkey, I guess. And we also give like a set of rules. First, you're gonna cook the vegetables, then you're gonna season the chicken, and so on and so on. And then the result is that it will give us the chicken, um, um, the cooked chicken, and everything. But with a machine learning algorithm, it's different. We're going to give it the input and the output. It's like, from this, I want you to make this. You find out how to do it. Why? Because we then want to give maybe new ingredients, and we just don't know how to start with an input like let's say the vegetables and the chicken. We don't know how to get to that output. So for that, we need the machine learning model to find out, right? And then we can use that program like that recipe that the machine learning model figured out, we're going to use it many, many times. Okay, so let's move on. So when do we use machine learning? We don't use machine learning for everything. And I don't know if maybe your students, maybe you are actually working in a company, but you will hear, I think it's going to be more common each time. You will hear that now everyone wants to use AI everywhere. You want to put AI everywhere, and you may hear your boss or your coworkers, "Oh, let's use AI. Let's do it. Can we use AI here?" And maybe that's not the reason, right? Maybe that is not sorry the tool to solve a problem. AI is not the solution for everything. So when can we use machine learning? We can use machine learning when the human expertise does not exist. So let's say an example for that would be sending uh, a navigation device to Mars. We have never been there, right? So maybe we send the little robot and it will start like learning on site because we don't really have expertise on that. There is also we can use machine learning when humans can explain their expertise. For example, imagine that you have to write down an algorithm explaining how to learn, how did you learn how to talk, or how did you learn to recognize a speech. It's very complicated. It's sometimes we just cannot explain how we learn. I don't know how to ride a bike. You can have an idea, but like explain it in a way that a computer can follow step by step. It's very difficult, right? I think yes, speech recognition could be a good example. Then uh, we can use machine learning when the models they must be customized and they have to adapt to a changing environment. So that can be, for example, personalized medicine. That can be a good example for that. And then the best application, or at least the most popular, or where they're really really useful, is when we have to analyze huge amounts of data or huge amount of rules, and it's so vast that us as humans we just don't have the time and the resources to do so. So let's say all the work on genomics, for example. So these are areas where machine learning is super useful. Is an amazing tool that is really changing the capacity of humans to solve very complex problems. And I'm very excited about how fast machine learning is evolving, because I really believe that in the future, in the near future, we can solve very issues like, for example, the cure of cancer. And if you can Google around, you will see some really nice progress that machine learning is doing in that particular domain. But machine learning is not always useful, and us as developers, computer scientists, data scientists, or maybe you are a student, it's very important to understand this. We don't need to use machine learning everywhere. Sometimes it's just not the tool. Sometimes you are just going to waste time, resources on trying to solve a problem with machine learning where it could have be solved in a better, in an easier, cheaper, cheapest. Oh my god, my English. You get the point. And a faster way, right? So, for example, you don't need to create a machine learning algorithm to convert dollars to euros. You don't really need to do that. There is a simple algorithm that you can create. Maybe you need an API to connect to the latest exchange rate, and that's it. So you don't really need machine learning for that. Obviously, this is a very simple example, but you can think of other can be complex examples of these where you don't really need machine learning. And please share those on the chat. That will be actually fun to read. And this is a very important tip that is actually, I think it's in the Google Machine Learning Principles or something like that. This is like a rule of thumb. If you can build a simple rule-based system, if you can write a very simple program that doesn't require machine learning, just do that. Don't overcomplicate the stuff. Don't do it because it's the cool thing to do. Every technology has its own objectives and its own goals, and they're meant to be for a particular domain. So always have that in mind. So let's have a look at other machine learning applications. So this is a very classic example that really requires machine learning, which is identifying handwritten text, right? And in this case, these are numbers. And let's say number 2, you can find there a bunch of different examples of handwriting, and we recognize the number 2, but the ones that are on red, on the red squares, we're not sure if that is a number 2, is a 3, is a 7, what is that? So that is, as humans, maybe you contextualize the number and maybe that way you understand which number is. But if you really have to write, let's say, a rule-based system, an algorithm to recognize a handwritten number 2, how would you do that? You will need to look at attributes, right? Maybe the top is a curve. Maybe, I don't know, it has to be a little bit more horizontal by the end. Maybe it has a loop. It's so difficult. It's very difficult. So this is a perfect example of machine learning. What we do is that we collect a bunch of hand text and we provide it, and we say these are 2s, these are 3s, and we are gonna talk about that later, because that's a way of a type of learning. And then you provide that to the model, and the model learns and extract patterns and is capable of recognize the number that a new number that is not in the training data. So for example, I remember when I was studying AI, this was the first project that we did with neural networks. And we had to go, and just to give you an example, uh, that was the time where, I don't know if you remember the palms. There was like these devices that were called palms. Like the cell phones were not what they are right now, and um, that handwriting recognition of characters on the palms was something really new on the devices. So what we did was, like, we had to go and ask. I went and asked a bunch of friends, can you write numbers from 0 to 9, several lines, and give it to me? And I had to collect a bunch of those, and then we had to scan them, and then you had to separate all of the zeros from a lot of different people and tag them. This is a 0, this is a 1, this is a 2, and then you provide that to the model. And the model back then, nowadays is like almost instantly, but back then I think it took like a whole weekend to train the model in order to recognize this. So this is a good example where you can understand, okay, we cannot really make a program in the traditional way to recognize one number. Having a bunch of examples is the best way to achieve this goal of recognizing a digit. All right. So these are other examples of tasks that are best solved using machine learning. So as we said before, recognizing patterns, very good at it. Facial recognition, handwritten or spoken words. For example, when we're talking to Alexa and Alexa replies, and so on. Medical images. Machine learning is progressing so fast and so good in this domain. Um, there was a competition, I think it was in China, where it was two teams, the machines versus the radiologists. And they gave a bunch of images of, um, yeah, radiographias. I'm trying to think about the name in English. Probably it's a very simple name. A bunch of images, X-rays, and they had to find a particular, yeah, the right radiologists are the doctors, but they had to find certain things on the images, and the machines were way faster and way were more precise and correct than the medical doctors, and that was awesome because uh, that is not something that should worry us, like, oh, the doctors are going to end up without a job. It's not. It's just that um, it's going to be it is already such a great tool for the doctors to be more precise on their diagnosis, and to help the patients faster, less prone to errors, and so on and so on. So yeah, it's a great way to it's a tool. So yeah, John is saying that he still wants to ask a doctor to confirm. So yeah, I guess because it's a tool, it's always good to for the doctor to check. Okay, this fine. I agree, or whatever. I always also tell this story. My father-in-law was here in Scotland visiting last year, and he's diabetic, and I had to take him to the hospital because he was having problem with one of his eyes, and I went there to translate from English to Spanish, and I was seeing the doctor doing this test on the back of his eye to find it's called diabetic retinopathy. And I remember a study that Google was part of that, to help the doctors to find out very early this particular disease. And I asked the doctor. I was very excited, right? And I asked him like, "Oh, so have you been using AI for this?" Because I told him I saw this by Google, and he was super excited. And he actually told me that yes, they're using it, and that he thought it was remarkable. That's the words he said. Why? Because the model was able to scan these images that are from the back of the eye, and it was able to recognize very early signs of this disease, and it was also able to recognize other attributes or other features such as the age of the patient, but the age was very precise. um, because he told me we are able to, like the doctors, they're able to identify if the patient is a kid or if the patient is a middle-aged person or maybe a senior person. But they're not able to identify the age. They don't know what to look for. They don't know what is the pattern to look for. But the model knows. And it can be something like the patient is 37 and the model says that is 36. It's very precise, very near the right response. And he told me that it was remarkable because they really don't understand, but the model is right. So machine learning is very good at recognizing patterns, and it's better than us. All right, so let's continue. Generating patterns. The That is our the most popular application of machine learning nowadays. For example, ChatGPT, the generative AI, generating text, generating images. It can be ChatGPT, Bard. We can use Midjourney, DALI, motion sequences, movies, and so on. It's very good at this. It's gonna get better, and it's also exciting. Sometimes it's a little bit frightening, but it's in terms of how we responsibly use these technologies. And we're going to talk a little bit about responsible AI by the very end of the whole bootcamp. But yeah, machine learning is very good at this. Also to make predictions, uh, because given a bunch of previous data, it can be very good at predict um, an outcome, right? And also very good at, since it can recognize patterns, it can be very good at recognizing anomalies out of the expected patterns. So for example, we can use machine learning in cybersecurity, um, for credit card transactions, for example, unusual patterns of sensor readings, and a bunch of other applications. So machine learning is again a very interesting, fun, and useful domain and skill to have nowadays. And it can be something, again, like I told you before, uh, in, let's say, by the beginning of 2000, maybe in 1995, um, everyone was very excited about web technologies. Everyone wanted to learn web technologies. uh, the students, the software engineers, they all wanted to learn that, and some of them, they made millions out of it. And it was like the boom, the best thing in tech, and it really changed the course of humanity, right? The way the world works right now is very, very different as how it was before the internet. So for machine learning and artificial intelligence, I believe it's the same. Um, it's evolving so fast, and is getting so good at so many things, that I really believe that this is the moment where all of you should have a look, should have you should learn about it, learn those skills, because this is going to permeate every single aspect of humanity. So I'm pretty happy that you're here in the boot camp, in this boot camp, and I hope that this is going to be like your first very step into the world of machine learning and into a really nice career in this area. All right, let's continue. A little bit of fun story. So the first machine learning application, and it was created by Arthur Samuels in the late 50s. And it was one of the very earliest self-learning programs. So he said, or defined machine learning as a field of study that gives computer the ability to learn without being explicitly programmed. So this was like the very first instance where a machine started learning by itself. So he used some machine learning techniques to improve the way the machine was playing checkers, and the way it learned was playing by itself several times, and each iteration would make the machine to play better and to learn, and it will get like more skilled into the game. And by the end, it got really good at it, and it really could actually defeat human players. And it really was like it paved the way for the future developments in machine learning and artificial intelligence. It was a very, very important point in the history of machine learning and artificial intelligence. And it was incredible because it demonstrated the capacity of computers to actually learn and adapt in an autonomous way. And that was something that it was very sci-fi. It's still a little bit very sci-fi. So yeah, I would recommend you to have a look at this story. Maybe Google it. It's really fun. Okay, so now let's talk about the types of learning. So now we are going to get into the interesting parts of machine learning and the technical side of it. Again, today is going to be an overview, but we're going to actually work with code, and we are going to work with models that use these types of learning. So the first one is supervised learning, and this is a technique that um, relies on having training data that is labeled, and each data is obviously related to the output value. Okay, so we're going to see also a simple example so we can understand it better. So the goal is to train a model that can accurately predict or classify new unseen data. Okay, so let's see what does this really mean. So let's see this example. Let's say that we want a machine learning model to classify if something is an apple or a cupcake. All right. So what we're going to do is that maybe we can go and take pictures of a bunch of different apples and a bunch of different cupcakes. Why do we want it to be different? Because we don't want the model to recognize just one. Like we want to get different types of attributes, um, different values for the common attributes, right, of that object. So if we always show the same apple, it's going to be harder for the model to recognize a different apple, maybe an apple that has a different shade, or the color is a little bit different. So we're going to get a bunch of different cupcakes pictures, a bunch of different apples, and we're going to say, this is an apple, this is a cupcake, this is a cupcake, this is an apple. We are basically teaching like a kid, right? And we give that data to the machine learning model, and it will learn during a process that we're going to learn in more detail. And then when we give a new image that is not on our training data, an image that it has never seen before, let's say a cupcake, and we don't say this time this is a cupcake, we just show the image, or we use the image as an input, the model would say, oh, this is a cupcake. Okay, so we're giving training data plus the desired outputs, which is the label. I want this to be a cupcake, and so on. This is supervised training. So in order to understand a little bit more about this, let's talk about the features and the attributes of a class. And when we talk about classes, we are talking about, for example, this machine learning model, this one that we're seeing on the screen, it has two classes. One is apples and the other one is cupcake. All right? All right. So let's talk about the attributes. So the attributes or the features, we're going to be talking a lot about features and attributes during the whole bootcamp. Um, so the features are the things that we use to train the model, right? Are the properties of the things that we want to learn about and predict. So for example, about the apple, we can have two attributes. We can say, well, the weight and the color. This apple, the weight is 250 and the color is green. We can have another apple that maybe is a little bit um, lighter, and it's, I don't know, 150, and then the color might be red. But if we have a bunch of different apples and different values, that's going to be actually better for the model. Let's see, I'm going to do some stuff here to read the questions. What does labels mean here? Why labels can be regarded as output? Okay, I'm going to roll back a little bit. So the output, if you output is the label is cupcake, what do you want the model to do? Let's think about the problem. Okay, we want a model that recognize apples or cupcakes. That's what we want. And we want to bring maybe we want to bake a cupcake, and we want to throw it in the model, and for the model to recognize if it's a cupcake or if it's an apple, right? So those are the outputs. It can be apple, it can be cupcake. those are the outputs of the model. Okay, so why the labels are the outputs? Because the labels are when you're training the model, when you're building up your training data set, you will have two classes, right? Apple and cupcakes. And you're going to have a bunch of images of apples, images of cupcakes. And you want to teach the model by saying, this is an apple, and that's the label. This is an apple, this is a cupcake, this is a cupcake, this is an apple, and so on. That's why the labels match the output, because that's actually what you want to know. You want to know if that object is one of those two classes. Hopefully that makes sense. Uh, Liz is asking, I have always wondered why we need a large quantity of images for a fairly uniform item. Example, coffee cup. Okay. How many images are enough for training the model? Okay, that's a very good question. Why do you need large quantity of images? Well, that really depends because, for example, if you have trained your cell phone and it has the facial recognition for lock and unlocking the cell phone, for example, right? Your face is the same; it's always the same. But when you're training the phone to recognize your face, it tells you to move your face a little bit, maybe a little bit to the sides, maybe looking up, looking down, because you're not going to use a cell phone every time. It's not going to be like the same picture, like a picture of your front. Maybe you're moving your head a little bit. Maybe you're seeing the phone from the way up. So that's why you have like the most data that you give as an example, the better, because it can help. It will perform in a better way. Of course, because in terms of the images, for example, coffee capsules, all same shape and size, is different color or pattern. Yes, you need to do it because maybe that picture, the picture that you're going to use as an input, is going to be shot in a different lighting, maybe in a different perspective. So that's why the you need variety in your training data set. But of course, there is a top, right? How many images are enough? That really depends on many, many things. And one is when you're training your model, and we're going to talk about that later. When you're training your model and you get an output, you actually use some testing data, right? You want to test how the model behaves and if the output is actually correct and is what you're looking for. And the testing data is different than your training data, right? The model never saw that data before. And if you see that the output is correct, you can use the model like you can leave it like that. But if you see that it's incorrect, you have to train it again, and maybe you have to use more training data, or maybe you have to adjust something on the model. It can really depend. And it also depends on the resources that you have and the regarding the computer power that you need and so on. But we are going to talk about that later. But it's a very good question, and it's a question that everyone has. Um, Sounds like give the machine guess range. No, not really. But we're gonna when we go to do the coding and the practical side of the bootcamp, I think you're gonna understand a little bit better this part. Okay. Uh, so we were talking about the features. So right, these are the features. So for example, for the Apple, we can use this feature. We can add another feature. I don't know, number of leaves, or it can be anything. Uh, let's think about other kind of let's say, for example, a face can have different features. It can be or a person, the color of the eyes, the color of the skin, the length of the hair. There can be many, many different features, and you can use that on your model. We're gonna work a lot with features on the practical exercises, and you will see how we work with it. Okay. Let's have a look at this. So I want to give credit for this graph to Jason Mays, which he's a web machine learning lead in Google. And he's amazing, and he's always producing amazing content for all of us. So credits to him for these graph. So in this example, let's say that we want to classify apples from oranges, right? And we're going to use two features, which is like we saw before, weight and color, right? And because we're using two features, if you see in the graph, we have on the y-axis weight and on the x-axis the color, right? And then we have there all of the different points, data points for our apples and our oranges. So maybe the color of our apple is near here, but the weight is this one. And then the oranges, we have them a little bit here in terms of the color, but maybe they weight a little bit more. And then we can do like a classification on how to separate these in clusters, but we're going to talk about that later. But the main point of this is that I wanted you to see how we can represent and start playing um, and start thinking about how can we maybe have a kind of an algorithm for solving this issue, right? And if we use this kind of graph, it could be very easy, right? We can say, well, if the color is near here and the weight is near here, maybe we can just know if it's an apple or not. So this is very simple, but of course it can get complicated, but it's very important for you to understand this because it's the very basic of this particular way of solving machine learning problems. So if we have two features, is a simple 2D system that we can plot on a graph. If we can represent that in a numerical way, and actually, um, everything that we do in machine learning is going to be represented in a numerical way. All right. Now let's talk about unsupervised learning. And unlike supervised learning, which was the one that we saw before, unsupervised learning, it really doesn't have a predefined target variables. And the model, really what it does is that it explores the data to find insights and patterns. So again, we are not going to give any kind of labels for the training data set. And because of that, because we're not given any kind of label, we're not given an output. And it will discover relationships, pattern clusters, hidden patterns that we don't really see. So let's see again the example with the apples and the cupcakes. So what we're going to give is a bunch of unlabeled training data, right? As you can see there, a bunch of apples and cupcakes, but we are not saying that this is an apple, this is a cupcake. We just are giving all of that, or let's say pictures, all of those pictures. And then the model, using certain techniques that we are going to be reviewing on the during the bootcamp, it will interpret the information, it will work on the algorithm, and it will process, and then it will separate the information in clusters maybe. So these are the apples and these are the cupcakes. Okay, so that's what in a very high level overview unsupervised learning does. So this is what we are going to cover today, um, um, because this lesson is just about the basic concepts. And starting next week, we're going to talk about all the different types of machine learning algorithms, and we are also going to talk about how to prepare the data, how we have to play with the data in order to make our model more optimal, and we are going to actually work with code. If you have any question, something that you would like to follow up, uh, as a follow up, can I still access autonomous fiber? So if it's still yeah, I can help you with that, Liz. Does anyone have any question before we wrap up today? Remember, we will continue next week. And next week lesson is going to be 2 hours. All the other lessons are going to be 2 hours because we're actually going to code. But this is the main content that I wanted to review as an introduction of the basic concepts of machine learning. If you have any other question, thank you so much for being here. I'm really excited. I really hope that you will enjoy this bootcamp and that we will be making this really nice group for the rest of July and learn a lot. I'll be around in the Discord channel, and yeah, we're going to be what I want you to know is that today is very basic, a very basic overview, but the complexity of the stuff that we are going to be doing is going to get higher and higher because by the end of the bootcamp, I want you to live with the working knowledge on how to create a model, right? And you are going to actually code and create your own machine learning models, and you will have the base to be able to keep on learning and keep on walking through the journey of machine learning and actually create very fun and hopefully useful stuff for people. All right, well, thank you, everyone. I will share the slides and I will also share the recording for today's session. And I hope to see you all next Friday. Thank you and have a great weekend. Bye bye.